Hello, welcome to our seventh KCS talk for this semester. Our speaker today is a new faculty member, Dr. Haibo, Haibo Wang, Haibo Wang, okay. And the title of, as you can see, the title of his talk is Sketches for Network Traffic Measurement from Fundamentals to Recent Advancements, okay. And he will explore the development of sketches in capturing the fundamental statistic of flow size, charting the course from basic principles to the most recent advancement. Okay, let's welcome the speaker for today, Dr. Wang.
Thank you. Today we'd like to welcome to my talk, and I'm honored to be invited. Today I'd like to introduce sketches, which are fundamental and emerging solutions for network traffic measurement. And we will go from the fundamental designs, fundamental sketches, to the most recent ones. So first, we will give an overview of sketches. So we begin with an appetizer, where we want to measure the ball appearances. We have 10 balls. We have 4 colors. We want to measure how many balls in each color. So, a straightforward way is to have 4 bins, right? And for each ball, we will go from the first bin, find out the first empty bin, or find out the bin with the same color. All right. So for the blue ones, it will go to first empty bin, and for the yellow ones, it goes to first bin. It's not empty. It already stored the blue one, so it will go to second one. So for the third one is blue, so it goes to first bin. And we do that for each one. And these solutions, we need 4 bins, and we need at most 4 bin axes per ball. Okay. But imagine that we need 1 million bin, 1 million colors, okay, with more than 1 million balls. In this case, with these solutions, we need 1 million bins, and for each ball, we need to access at most 1 million bins, because we need to find an empty one or find the one with the exact color. Okay, and this is a linear time, linear space solution. We need, for n colors, we need n bins and on bin access. We have a better solution of hash table, where we have 4 colors as well. In example, we perform hash on the color of the ball. Let's say the hash value of the blue one is 1, and the yellow one is 2, the red one is 3, and the green one is 4. So for each ball, we hash on its color and map that ball directly to the bin with the index of the hash value. So with the blue one, it will go to first, the yellow one directly goes to second, and the orange one goes to third, and the green one goes to fourth. So this will be a linear space and constant time solution, because if we have n colors, we only need n bins, and we only need 1 hash, 1 bin access. But sometimes the hash value is not that good. Here there is no clear. Sometimes there will be the same hash value. Let's say hash value of the red one is 3, and the green one is also 3. So there will be some hash clearance. So we relax the number of bins we used. We don't use n bins. We may use 2 n bins, 3 n bins to alleviate the hash clearance. And the amortized bin access will still be constant. Okay, so it's linear space and constant time solution. And sketch falls in another scope. We have a sublinear space. That means the number of bins we have is much smaller than the number of colors, usually much smaller. So it will allow balls of different colors to share bins. So a bin may accommodate balls of different colors. And because of the bin sharing, there is approximate estimation. There must be some error. But this is the open area. We need to improve its accuracy. It's constant time update for each ball. In network traffic measurement scenarios, we need to model the network traffic as flows, where the ball will be the packet in the network. And the color of the balls will be the flow label carried by the packet. In the packet header, flow label can be any fields in the packet header. It can be source IP, destination IP, port number, or their combinations, depending on the application need. You can arbitrarily set. And the balls of the same color will be a flow. And the packets carry the same flow label will form a flow. So the number of balls with the same color, with the ball appearances, will be the flow size, will be the number of packets in the flow. So it's the first flow statistic we introduce. There are numerous of flow statistics, and there are numerous of traffic patterns in network. We have flow size, we have introduced it. We have the flow's cardinality, which is the flow's distinct values. We can have the heavy hitters, large flows, super spreaders, and other flow statistics, flow entropies, and flow distributions. We can have different traffic patterns like burst or the heavy chains, and so on. We measure those flow statistics and patterns because we find in applications, practical applications, we need to measure them. So we design sketches. And besides, when we find out a flow statistic and pattern we need to measure, we also need to consider the system setting. For example, whether we consider the sliding window model or fixed window model, whether we use the common sampling techniques or not, we use only the on-chip high-speed memories, or we combine the on-chip high-speed memories and off-chip memories together. And we probably want to design a generic solutions or specific solutions. So this talk, we only focus on first statistical flow size, and we use the basic setting, system setting. And in this narrowed scope of flow size measurement in basic system model, there are two categories of solutions. The first one is a generic sketch framework, and the second category is the efficient counters in the framework, which will be introduced in the second part and third part respectively, which are detailed and reviewed. Yeah. And before we move forward, we want to give an example data set and the performance metrics to show how you evaluate your performance. We use the 1-minute CADA data set from CADA, which is downloaded from switches of a US backbone networks. It contains 20 million packets and 430,000 different source destination pairs, and thus the same number of flows if we consider source and destination IP pairs as a flow label. We want to stress that in network traffic, the flows distribution, size distributions are heavily skewed, meaning that most flows are really small and only a few number of large flows, but they account for most of the traffic. If we see the right table, we separate flows into different ranges based on their flow size from 1 to 10, 11 to 100, 101 to 1,000, and so on. You will find most flows, their average size will be from 1 to 10. And only over 200 flows are large flows whose size are larger than 10,000. So it's heavily skewed. We use the identical memory allocation of 1 megabits, which means that each flow on average can occupy 2 and 3 bits. This will be in the scope that previous hash tables cannot address. Okay. We consider 2 performance metrics. The accuracy one, which is obvious. The second one is the processing overhead. We want to know how fast the sketch can process the packet stream. And it can be measured by the processing time per second or the meaning packets per second we can process. Now we go to the first category of sketches. The first one is a generic sketch framework, and the first solution is a count-mean sketch. This is a very classical sketch. You can find it in nearly other areas. Okay. Its data structure is an array of W counters, illustrated on the right. And for recording, upon an arrival of a packet, we will extract its flow label, which is F. And we will hash the packet by the flow label to the HIF counter in the ith array. So each packet will be hashed to D counters, each in an array. And we will increment the counter each by 1. So 4 will be 5, 2 will be 3, and 7 will be 8. Because other flows, noise flows, let's say F prime, can also be hashed to the same counter with F. So the counter's value will be further increased by F prime. So there will be overestimation. And because of overestimations, all the counters will be larger than the flow's real size, any flow's real size in that counter. So we return the minimal one because it carries the minimal value or minimal error. It will be more accurate. So the count-mean sketch in the performance using our example data set, we set the D to be 4. So each packet will be hashed to 4 counters. So each array will have 8,000 of counters. So on average, there will be 54 flows per counter. So that means each flow in its hash counter, it has to share that counter with 54 flows. And the average noise introduced by the 54 flows will be 2,500. Okay, so this is the base noise level. Using our count-mean sketch, we first look at the average absolute error. For flows in different ranges, you will find its error is around 500. For small flows, in 1 to 10, it's 488. For large flows, it's 522. So it's around 500. And if we look at the top 20 largest flows, the first column is the real value. The second column is the estimates. You will find that for the largest one, for example, it's 130,675. And the estimate is around 400 overestimation. And for each flow, its estimate will be larger than its real value because there will only be false positive. There will only be overestimation. So this average absolute error are all about overestimation. So we reduce the average noise level from 2,500 to 500, reducing like 80% of the error by the count-means mean operations. Okay, we return the minimum one as the estimate. So its processing throughput is around 3.88 million packets per second, and the per packet processing time is the inverse. And now the second one is conservative update. We call CU. It's an optimization based on count-mean. It has the same data structure, exactly the same, but instead of the increment each of the D hashed counters by 1, which count_min does, it conservatively increments the minimum counter by 1. So in the example, there will be 3 hash counters, this counter, and this counter. And the minimum value, which is 2, will be increased by 1 from 2 to 3. And other 2 hash counters will remain unchanged. The reason is that all the counters has false positives. So the minimum one carries the minimum noise. We only need to increase this one. We don't want to deposit additional noise to other larger counters because they already carry more errors. So returning the minimum one, which is the same as the count mean, will be its query operations. The CU is performance. It has a similar performance with the same parameter settings, the same errors, the same number of flows in hash collisions, and the same average noise level. If we look at the average absolute error, it can reduce from 5,000 of count mean to 300, or 500 to 300, 40% error reduction. And moreover, the most important is it can significantly reduce the error for large flows. It can reduce the average absolute error for large flows from 522 to 5.5, which means on average for large flows, there will be overestimation of 5.5. So if we still look at the top 20 flows, you see the first flow is real value 130,635, and it's estimated 130,679, only an estimation of 4. Okay, so it's a very precise estimation. For the second one, it's an overestimation of 4. For the third one, it's an overestimation of 16. And for the fourth one, it has no error. For the fifth one, it has no error. Sixth one, it has no error. Okay, so CU is extremely accurate for large flows and can improve the accuracy for small flows based on count mean. Its processing throughput is slightly slower than count mean because it needs to find out the smallest ones and increment the smallest ones. So there will be additional operations. And the third one, which is still a multi-update sketch, which means a packet will be mapped to multiple counters. It's the same data structure. All of them have the same data structure. In recording, we hash the counter to D, hash the packet to D counters, and now we don't always increment that counter by 1. We increment the counter by 1 or decrease it by 1 with equal probability, depending on another binary hash value on the flow label. Okay, so for the first counter, we could increase it from 4 to 5 or decrease it from 4 to 3 with equal probability. For the second one, from 2 to 3 or 2 to 1 with equal probability. And they are independent in array-wise. So because the noise flows, there are numerous of noise flows, will be mapped to the same counter. So you can see this noise flows has equal probability to increase the counter or decrease the counter. That means we can expect half noise flows to increment the value of the counter, and the other half to decrease the value of the counter. So the overall impact of the noise flows will be canceled out. So the counter actually is an unbiased estimation. And by returning the median ones of these D counters value, we can further reduce the variance. So count sketch with the same settings, it can reduce the noise flows, the error for small flows from 500 of count mean, 300 of CU to 200 of CS, of count sketch. And for large flows, it can reduce 140 from count mean, but it's not as good as CU. Actually, CU is the best. We can hardly beat that. if we look at top 20 flows, the first flow is 100 overestimation. The second large flow is 800 underestimation. So there will be some overestimations, there are underestimations because it's unbiased. Okay, its processing throughput is still pretty much the same as count mean, but slightly higher than count scale than CU. And previously, all three generic sketch frameworks are all multi-update sketches. A counter, a packet is mapped to D counters, and the throughput will be small. Okay, and the fourth one is randomized count sharing, RCS, which is still the same data structure, but it's single update sketch. That means for each packet, we don't update D counters, but one counter. We randomly select one array from the D arrays by generating a random number from 1 to D, which is R. And we increment the mapped counter in the Rth array by 1. Okay? So for a flow, its packet will be updated in only one of the D counters, but a flow is mapped to D counters. In other words, a flow is split into D parts. Its packets are split into D parts, and each part goes to a counter in an array. So if we sum up those D counters, that will be the estimate of the flow. And we can the design of randomized counter sharing allow us to statistically calculate the average noise. So we can subtract the average noise of N over W, where N is the total number of packets, W is the number of counters in each array. And our experimental results, we actually have the same number of noise flows. Okay, its error can be large. Okay, its accuracy not as good as previous multi-update sketches, even worse than count mean. Count mean is 500, is 700. And for large flows, it's also worse. But its processing throughput is much higher, 4 times higher on average. And the per packet processing time is 4 times smaller. Okay. So on average, the previous multi-update sketches, count means, CU and CS, they are better than average error. Okay, their average absolute error are small. But RCS is good in per packet processing time. Okay, in this plane, where the x-axis is the average error, y-axis is the per packet processing time, we want the solution to be as close as to the origin point. So the next part is efficient plug-in counters. So the previous generic sketch designs, they use by default, they use regular counters, which is, let's say, regular counter with b bits. Then the counting range will from 0 to 2 to the power b minus 1. If we have a sign bit, that will be divided by 2. Okay. And for a 12-bit regular counter, in this example, its value, if it's 001, 001, 00101, it's binary representation, and it will be converted to 293. Okay, we usually need to set b to be 32 to accommodate sufficiently large estimation range to the 2 to the power of 32. Okay. But active counters are more memory efficient. It contains 2 parts. The first one is the base part and the exponent part. Okay, so the value of the active counter is interpreted as base part times 2 to the power of exponent part. So when we're recording a packet, every time we increase the counter by 1, we will increase the base part with probability of p, which p is adjusted depending on the value of the exponent part. It will be 1 over 2 to the power exponent part. Okay. And if there is overflow, we will do some additional operation. The advantage of the active counter is that it has a very large estimation range, even with a small bit. We don't need 32 bits. We can use a 16 bits. If we use a 5-bit base part, 5-bit exponent part, in total it will be 10 bits. We can count the estimation range to the 31 times 2 to the power 31. Okay. In the same binary representation as this one, as a regular counter, if we use the first 7 bits as the base part and the remaining 5 bits as the exponent part, its value will be 288. Okay. It's not the same as 293. That means the active counter, it has larger estimation range, but it has coarse granularity. So in the experiment, if we test the flows with different sizes, the flow size from 0 to 10 million, okay, and we use 8-bit base part and 4-bit exponent part, we will find initially the relative error, which the y-axis will fluctuate a lot, but gradually it will around 4% of relative error. Okay, that means with these parameter settings, it will be 4% of relative error. If we increase the base part from 8-bit to 12 bits, so in total there will be 16 bits, which is this point. In this case, we will reduce the relative error from 12 bits, which is around 4% or 3%, to 1%. Okay, which is a pretty small estimation error. So if we apply active counters in Sketch, okay, we add plugins. We don't use regular counter now. We use 16 bits. We will find the active counters in different sketches. They can improve the accuracy for count mean for each generic framework. For count mean, for small flows, it's 488. But with active counters, it's 166. And for large flows, count mean is 522, and for small flows, for large flows, is 231. Okay. It can reduce the error for nearly all generic sketches, but not CU, because CU always update the smallest one, while because AC perform probabilistic counting, you always use the smallest one will make it's by underestimate. Okay. So we find, if we see the plot, you will find with CAC, CUAC compared with CU, CMAC compared with CM, CSAC compared with CS. You will find with active counters, you can always drag the generic sketch to the left top direction. That means active counters can reduce the average error, but it incurs slightly, sometimes severe per packet processing overhead, especially for CU. Okay, but CU is not very good in this example. Even for RCS, it's the same. So the second one is a self-adjusting counter. It starts from a small regular counter with 8 bits. So it's from the estimation from 0 to 2 to the power of 8 minus 1, so it's 255. So the small active counters can easily overflow. When it overflows, we will merge adjacent ones with some operations. That means if we have a 8-bit small counter, will be merged to a 16-bit counter and then 32-bit counter. And the advantage of self-adjusting counter is that it can perform exact counting. Okay, it merges adjacent counters, but it always performs exact counting. There will be no probabilistic counting. And there will be some additional indicate bits to indicate how we interpret the counters. If we have 4 counters, which means we have 32 bits memory block, okay, 4 8-bit small regular counters. There are 5 types of interpretations. It could be 3 4-bit of 8-bit small regular counters A, B, C, and D. It could be the 16-bit counter merged from A and B and C and D. It could be a 8-bit counter A, 8-bit counter B, and 16-bit merged from counter C and counter D. And it could be A, B, C, D, which means 2 16-bit counters. And it could be a 32-bit counter merged by A, B, C, and D. So with 5 types, we need at least 3 indicate bits. So on average, usually we will implement 1 bit per counter for indicator, but it can be optimized to be 0.6 bit. Okay. So when we merge, in the example, there are 8 small counters. That means the total memory is 64 bits. When we want to increase the counter 1 from 255 by 3 to 258, we will merge, because it's about overflow, we will merge adjacent ones. We will merge count 0 and count 1 and make it a 16-bit short counter. And if we want to merge a short counter from count 4 to count 5, and we will merge it to be a 32-bit counter. And because the network traffic is heavily skewed, so large flows only occupy a small number of counters, and thus the merge operations will only happen for those large flows. Okay, most small flows will experience small counters. And if we use self-adjusting sketch, counters in sketch, we will find there is always memory accuracy improvement. And if we compare with the active counters, you will find it's better than active counters. Okay, slightly better than active counters. And there are also another types of counters we call CED-AR counters. It's another types of design, which means it provides scalable counter estimate. Let's say it use regular small counters, okay? So it will be less than 32 bits, but its counter range will be at least 2 to the power 32. So for any counter, its value is I. In regular counters, we will think the counter is I, the estimate is I. But for CED-AR counters, it's not. If a counter is I, its estimate will be AI, where AI is a function of I. And AI is usually much larger than I asymptotically, especially when I is large. And in this way, we can provide much larger estimates. So in recording, we increment the counter from the value I to value I plus 1 with a probability of 1 over I plus 1 minus AI. So in the example where we have 3 bits, because we have 3 bits, the I can only be from 0, you see the subscript, to 7. And A0 is 0, A1 is 1, A2 represents 4, A3 represents 9, and A7, which is the maximum one, can estimate, represent a value of 211. So it will be a much larger estimation range. If we want to increase the counter from I to 0 to 1, we will increase it with the probability of A1 minus A0, which will be 1. And if we want to further increase it from 1 to 2, because A2 represents 4, the value of 4, and A1 represents the value of 1. So we will increase it to 2 with a probability of 1 over 3. And do that for, that will be 1 over 5 if we want to increase it from 2 to 3. The CEDR counters is also a probabilistic counting. Okay, we use a 12 bits, okay, which is recommended. We can find it's also an improvement for the based on the regular counters. So, and there are many other counters, efficient counters like self-adapting counters, adaptive counters, and other counters. And we find the blue circle, which is a multi-update sketch with regular counters in the middle, and the green lines, green circles with the efficient counters can drag the general sketch to the left top. And then the red one is a single update sketch. So our solution, we propose a SSVS sketch. Our goal is that we want to start with the single update sketch because we know the multi-update sketch is inherit the multi-updates property. So we can hardly change that. That means we can hardly reduce its packet processing time. So we start with single update sketch, and now our goal is to drag this red circle to the left bottom. So we just need to reduce its accuracy, reduce its error, improve its accuracy. So our goal is our logic is to use one single counter per packet update. And we use some efficient designs, efficient counters, and other designs to improve its accuracy. So we first begin with a new single update sketch. We don't inherit the randomized counter theory at RCS. We did some changes. For each counter, it's the same data structure. For each packet, it will be randomly selected to an array R and hashed to the packet to a counter in that array. But now we borrow the idea from count sketch because count sketch is unbiased estimate. We increment that counter by 1 or decrease that counter by 1 with equal probability. So this counter, it will be unbiased estimate. We directly get unbiased estimate instead of subtracting the statistical noise from RCS. And for query, we will sum them because each flow, it will be split into D parts and be hashed to D counters separately. We sum them up, and that will be the estimate. And we propose a variable counter design, which is a new efficient counter. It's only 16 bits with an additional indicator of I of 2 bits. So total, there will be 18 bits. The I has 4 types of interpretations. If it's 0, it will be, the 16 bits will be 2 8-bit counters. If it's 1, it will be 16-bit counter. If it's 2, it will be a small active counter, which has a 12 base bits and 3 exponent bits. So the exponent bit is small. If it's 3, it will be a large active counter with 10 base bits and 3 and 5 exponent bits. And we use the first bit as a sign bit. And if for a counter, it initializes at 0, if it increases to until 2 to the power of 7 minus 1, it's byte counters. Okay, so there will be very small 8-bit memory consumption, and there will be exact counting. And if it overflows, we will merge 2 byte counters as a 16-bit short counters to the range 2 to the power of 15 minus 1. Okay, and until that, it's probabilistic or it's exact counting. That means the counter itself incurs no error. And if it continue overflow, it will be a small active counter. Small active counter is probabilistic counting that has error, but we use small bits for the exponent part. That means the probabilistic counting will have smaller error. So this adaptive design will help to the counter to have memory efficiency and exact counting for small flows, and small estimation error for small in this range, and for very large, we have to use a large active counter. They can count to the range up to the power of 41, very large. And we give an example of 4 counters, 4 variable counters, each is 16 bits, total 64 bits, and with different representations, okay, with different indicate values. But they all carry the first variable counter, the second variable counter. All these 4 variable counters have the same binary representation. If it's I is 0, then it's 2 byte counters. First sign 0, then it's a positive value, and the remaining 7 bits are the value part, so it's 18. And the second byte counter is sign is 1, so it's negative, and the remaining 7 bits are the value part, so it's minus 76. If it's I, then it's a 16-bit short counter, where the first bit is a sign, and the remaining 15 bits are the value part, so it will be 4,812. If the small counter, I is 2 is small counter, small active counter, the 3 bits will be exponent part, and the 12 bits will be the value part, and one bit for sign. So it will be around 9,000. And then for a large estimate, large active counter. And to handle the overflow, if it's 8-bit counter overflow, we will combine the 2 neighboring 8-bit counters into 1 byte short counters. And then if a short counter overflows, we convert it to a small active counter. Small active counter flows make it large active counters. In our process of handling overflow, there will be no error incurred. Okay. And we don't think the large active counter can overflow because it's too large. We have a new query method. The previous query method fetch the D counters and sum them, these D counters as estimate. But we find that because let's say a flow with a size of 200, so with D to be 4, there will be 4 arrays. So each hash counter out of the 4 hash counters will be increased by 50 or decreased by 50. But let's say we now have a large flow F prime whose size is 20,000. Then when they collide with this counter will be increased or decreased by 5,000. So this will be an outlier counter in the estimation. If we use that as part in some operations, there will be a severe deviation. So our method is to remove the noise outlier counters. We sort the D counters and get the 2 counters that are closest, because we think it's noise, the counters value conform identical distribution. If it's Gaussian, you will find the closest one will be in the expectation. So, and we define the counter as C and C prime. We define a noise interval from C minus a noise value and C prime plus a noise value. In this range, in this interval, only those counters in that interval will be included, and we will do scanning in estimation. And in our performance, we first compare the accuracy, where this is the average absolute error, where our proposed SSVS, the 2 means the new query method. If we find the small flows, you will find it's 60 average absolute error, which is the smallest among all existing ones. The bold ones are state-of-the-art. And for large ones, it's still one of the smallest, but not the smallest as CU. Yes, CU is so good that every country using CU is so good. But if you use the average value, average relative error, you will find the CU is so good that the relative error is so small, but our relative error is around 1.6%. We believe this is still in a low level. So we think its accuracy is adequate. And for per packet processing time, because SSVS inherits a single update sketch, so it has similar processing time per packet as randomized counter sharing, around 70 nanoseconds, okay, which is around 14 million packets per second. While others, the multi-update sketch will be at least 4 times smaller of recording throughput. Okay, so overall, we achieve a new sketch that is both low average error and low per packet processing time. Okay, so this will be the talk. Yeah, thank you for attending.
We have some time for questions, actually more than 10 minutes. So any questions for the speaker?
Thank you. So I have 2 questions. The first one is, what is the memory consumption for your variable counter method?
It's 16 for each counter, but the total memory in the sketch, when we plug that into the sketch, it will be 1 million bits, 1 megabits.
So is that a trade-off? So you're using more memory space for better performance and error rates?
Yeah, it's true. But firstly, that sketch are designed to address the problem of sublinear memories, which means the memory is sublinear to the number flow. So it is motivated by the application that in network there are too many numerous flows, while the on-chip memory is severely limited. So we can slightly relax the memory from 1 megabit to 5 megabits, 10 megabits. That's okay, but we cannot go beyond that because the available memory in for SRAM memories in network switches probably is in that order of magnitude, and it has disappeared by other functions.
Thank you. So my second question is actually a more general one. So where do you use the sketches? So do you use them in the router, or you're using in any monitor computer?
The sketches are used in network measurement scenarios. It will be used on the on-die memory of the switches. Okay, in programmable switches, that will be SRAM memories. But if you want to use in other scenarios, it's also for data streaming. For data streaming, it's also okay.
Questions? Many?
So when network speed get faster, then when you do this adaptive sketch, we will kind of not be able to keep up with how network was transfer. That actually whether your processing is fast enough because of you do this adaptation in this adaptive sketch. Did you consider this performance aspect of this, try to use sketch to do measurement?
Oh, you mean the depth to the line rate?
Yes.
Yeah. Typically, in our experimental result, it's 14 million packets per second. But as the bandwidth gets higher, probably we cannot catch it. So in this case, we can use some other techniques, like sampling or some other things. But actually, what we test is our local computers. We find its absolute value sometimes varies. If you run the experiment on a computer that you just turn on, it will be faster, right? But sometimes it will be lower. But we care about the relative ones. It's in this orders of magnitude. And sometimes if you want to really adapt to that, sampling probably is a good technique to be applied, combined with this one.
I have a question. That might sound stupid, but I don't mind, okay?
No, it's okay.
Now, all this testing or test whatsoever, can AI be used in those things so that you don't have to use human being to do this work?
Oh, yeah. This is something new, yeah. Actually, there are two new areas someone tried to explore. The first one is that we can, let's say we feed the data set to AI model, and the AI model can have some memories, and then it can classify whether this flow is a large one or small one. And this can help the sketch measurement. This is number one. And the second one is that, which hasn't been explored, but it's quite interesting, is to learn on the data summaries from sketch. Because AI learn the data from the raw data, but sketch is actually a data summary from the raw data, which you can learn if you can learn. And probably that's, but it depends on the performance.
So what's your prediction?
My prediction is that for flow size, it's not good, because there are some preliminary experiments that show, because it has very small input information, but for other types of statistics, it probably can be done. Because let's say we want to size, for flow size measurements, we increase the counter by one, we increase the counter by one, or decrease the counter by one. That's very simple and very simple information. But for other complicated data structure, for other flow statistics, it probably can be benefit from AI model.
All right, thank you. Any other questions?
Thanks for your presentation. So my question is, what is the motivation behind why we wanted to have this accurate information of the packet numbers in the flow? Because, for example, in the network, the packet loss is quite a common thing, right? Mm-hmm. And what kind of applications it requires to have the information of this accuracy? How many packets? I mean,
yeah, that's the answer.
Yeah.
Good question. Yeah. For let's say we have a flow size, there are many applications. The first one is if you want to do load balancing, you have to know the large flows.
Yes.
When there is a congestion control, you want to do flow rerouting, and you must want to select those large flows to do rerouting. You don't want to route small flows. If you want to find out large flows, you need to measure their size, packet counts. Actually, packet counts is a very important statistic that the current network uses net flows. The net flows have this kind of flow statistic. They count each packet. Okay.
Yeah, and also from the statistics the small flows, the packet numbers is quite different from the largest flows, right?
Yeah, it's small.
So perhaps a rough classification. For example, there are many applications and they do this traffic classification and to identify which flow is it. I mean, this rough classification, it perhaps already can help to do the traffic engineering. So I'm wondering if there is an application which evaluate different models you have presented and to see what is the impact to the actual application. So perhaps you spend a lot of effort in order to try to improve the accuracy of the packet counting, but perhaps this improvement might not have a very great impact on the application level.
Yeah, good question. First, measuring packet flow size is an important one. It's not important in applications, but also important in theory. Okay, we want to measure this basic flow statistics. The second thing that, sometimes if we know this flow is small, we might don't care if we measure it 100 or 1. Probably that's the same, right? But you can see that even current solutions, if the current solutions, there are still some, its average error probably is over 100. So we haven't reached to a level that we don't care about this accuracy anymore. Okay, we haven't reached this bottleneck. Okay, so now for the applications for small flows, yes, in network or for any other data set, sometimes we care about one kind of statistic called entropy. Okay, the entropy is related to overflow sizes, and yeah, this is an example. And with, for example, entropy, we can support any support us to find the anomalies for cybersecurities. So yes, in sketch research, I would say one is to we abstract the applications to a scientific problem. And we work based on a scientific problem to further reduce its performance or further improve its performance. Okay, continue doing that. Another is we start from the real applications and design practical solutions to solve that. Both, I think, are pretty solid research.